So in this video we're going to be discussing the half-life of reactions. So half-life is actually designated by the variable t sub 1/2, and it's specifically the amount of time it takes for the reactant concentration to decrease to 1/2 of its initial concentration. So 100% of the reactant to decrease to 50% of the reactant concentration. Now each different reaction order has a different half-life equation associated with it. So for example, if we look at a zero order integrated rate law, we know that the concentration of the reactant is equal to the negative rate constant times the time of the reaction plus the initial reactant concentration. And so if we're going to be solving for the half-life of the reaction, we can sub in the concentration at a time is going to be half of the initial concentration, and our t value here is going to be t sub 1/2. So rearranging and solving for t sub 1/2, we can subtract this initial concentration over to the opposite side, and then we can factor out the initial concentration of the reactant, leaving us with 1/2 minus 1 in parentheses, and that's going to be equal to the negative rate constant times the half-life. Now remember that 1/2 minus 1 is actually just negative 1/2, so multiplying this initial reactant concentration times negative 1/2, we get negative initial reactant concentration over 2 is equal to our negative rate constant times the half-life. And finally, solving for half-life, we divide by the negative rate constant on both sides, leaving us with the zero order half-life equation to be equal to the initial reactant concentration over 2 times the rate constant. And so from the integrated rate laws of the reaction orders that we typically see, such as 0, 1st, or 2nd, we can actually derive this half-life equation for each of the reaction orders. Now it's important to note that the relationship of half-life to the initial reactant concentration changes with reaction order. So we can see that for our zero order reaction, half-life is going to be directly proportional to the initial reactant concentration. However, for a first order reaction, the initial reactant concentration isn't present in our T1/2 equation, and therefore the first order reaction is independent of initial reactant concentration. And finally, when looking at our second order half-life equation, we can see that the initial reactant concentration is on the denominator, and so this means that initial reactant concentration is going to be inversely related to the half-life. So if we take a closer look into a first order half-life which is independent of initial reactant concentration, we can see that as time proceeds, the concentration decreases to 1/2 of the initial concentration. So for example, in this reaction, the half-life is 100 seconds. The reactant concentration started at 1 molarity, and after that 100 seconds, after the half-life is passed, it decreases to 0.5 molarity. Now after 100 more seconds have passed, so after 2 half-lives have passed, the reaction is going to decrease to 1/4 of its initial concentration, so 0.25, which is actually just 1/2 of 0.5, which was the concentration of the reactant after 1 half-life has passed. So ultimately we can see that the reactant concentration continuously decreases by 1/2 as each half-life passes. So overall, here's kind of a summary table of the rate law information that we know. We know that different reactions can be associated with different orders with respect to their reactants, leading to rate laws, integrated rate laws, which we can plot since they're analogous to y equals mx plus b, and ultimately these integrated rate laws we can derive the half-life expression. And the half-life expression for a zero order reaction, the initial reactant concentration is directly related to the half-life. For the first order reaction, the half-life is independent of the initial reactant concentration. And for a second order reaction, the initial reactant concentration is inversely related to the half-life expression.